Hello my dear students, this is Akash HD. Welcome to the ASD physics classes. Hope you all are doing really great. So students, in this video we are going to learn about the construction, working principle and important terms related to the moving coil galvanometer. In this video we will get the questions of why we are using radial magnetic field, what is the uses of a soft iron core and why this instrument is sensitive. Okay, so let's start the video. So under the topic moving coil galvanometer, the first we are going to learn about the construction. Before learning the construction, we should understand this thing. So here you can see very well, there is the one scale is there in which we will see the readings. There is the one pointer is there and we will see that this pointer is made up of the aluminum. Okay. After that, there will be one concave shape magnet will be there. One magnet means North Pole and South Pole both together. Okay. So, which magnet will be there? Please make sure that which shape? Concave shape. Concave shape magnet will be there. Okay. After that, there will be one soft iron core and this will be which material? Ferromagnetic material. So, mu r value will be greater than 1. Okay. And there will be one spring will be there that will generate the restoring torque when the current will flow through this coil. Okay, so what this spring will do, it will generate the restoring torque. Okay, so all these things are there, is it? So let's learn one by one. So here you can see under the construction, MCG means what? Moving coil galvanometer. Okay, so see, MCG consists of multi-turn rectangular coil free to rotate about a fixed vertical axis in a radial magnetic field which is produced by concave shaped magnet. So as I told you, this is the concave shaped magnet. See this one here like this. See, concave shaped magnet. What it is doing? It is producing the radial magnetic field. You can see here. This is the magnetic field. This lines you are seeing now, this is the magnetic field. These lines are going now, this is the magnetic field. Why? Because field lines will start from the North Pole and it will enter into the South Pole. Is it? So radial magnetic field is there, na? Having the center here, let's take for example, you can see just like a radius. That's why the name is what? Radial magnetic field. And let's see what is the use of the radial magnetic field. See, radial magnetic field makes sure that angle between magnetic moment M and magnetic field B is always how much here? 90 degree. Okay. So you know very well what is the torque formula. Torque equal to MB sin phi I will use here. See, the torque is given here what? Torque is given by MB sin phi. What is phi? Phi is the angle between magnetic moment and the magnetic field. So what will happen that here? What is the direction of the magnetic field? You can see very well. Now I have taken the different situations. In first situation, let's take here magnetic moment in this direction. Is it? So let's take here, this is the magnetic field B. After that, let's take magnetic field in this direction. So this is B is there. After that, magnetic field in this direction, this B is there. Different positions. Which position will be used depending upon where is the pointer. Okay. So let's take what will happen that here when the current will flow in the coil here. Let's take when the current is flowing. So when the current will flow in the coil, what will happen that here? This pointer will get the one deflecting torque tau d. At the same time, there will be the one restoring torque. Why? Because this spring will be water, spring will be twisted. At equilibrium, both of them will be water, same. But first, we will understand why this deflecting torque in this phi is always 90 degree. So remember that here, let's take when the magnetic field in this direction, current is flowing and pointer is somewhere here. So what will happen that here? The magnetic moment in this direction, to get the direction of the magnetic moment, curl your finger along the current, then thumb will indicate the direction of the magnetic moment, right hand thumb rule. So here what is the angle between magnetic moment and magnetic field? How much here? 90 degrees. Similarly here, at any instant when the pointer has moved, and let's take when it is here vertically. So magnetic moment is here, is it? This is the magnetic moment. And how much angle is there? 90 degree angle is there. Similarly, let's take here again, this pointer is moving somewhere here. So see, this is the magnetic moment, this is the magnetic field, how much angle? So radial magnetic field is making sure that at any instant, wherever pointer is there, angle between magnetic moment and magnetic field should be how much here? 90 degree. Is it? Kindly see very well. Now after that, we will see some other constructions. As I told you, see, a soft iron, that means a ferromagnetic material, mu r value greater than 1. This mu r is called relative permeability. It is a dimensionless number. Okay. So a soft iron cylinder is arranged inside the coil, which increases the strength of the magnetic field. Where is the soft iron core? See, this black color is there now. This is the soft iron core is there. Is it cylindrical shape? This is the diagram in a 2D, but if in case you are seeing 3D diagram now, it will be just like a cylinder like this. Okay, see. So remember that here, what is the magnetic field formula? Magnetic field formula used to be mu into H. This mu is the permeability of the medium. So see, please, we can write here mu naught into mu r, and H depends upon number of turns into current, is it? So this is the magnetic field is there. So here you can see very well, mu, I have written here mu naught into mu r, and H is what? Ni. This H is called magnetizing field. So let's take, if the current is flowing, some current is flowing, but I want a strong magnetic field. So this mu r value should be what? Very high. That's why we are using soft iron core. It will increase the magnetic field strength. Okay, great. Now let's see the third one. The motion of the coil is controlled by two phosphor bronze springs, one above and another below the coil here. Let's see here. See. So here you can see very well, like this one fixed axis is there. This side one spring will be there, and this side also one spring will be there. When this pointer will move, this spring will get twisted and they will generate the restoring torque here, is it? And they are made up of which material? They are made up of phosphor bronze material. Okay, some alloy is there. Why we are doing? To increase the sensitivity of the galvanometer. Okay, great. Let's take fourth one. See, an aluminum pointer moves on a linear scale with a 0 at its center and equal divisions on either side of the central 0 as shown in diagram, is it? So you can see here. Here we have drawn here the some, it is there now, some divisions are there. So let's take for example, this is 0. So this side equal divisions will be there. Let's take for example 1, 2, 3, 4 for example. This side also 1, 2, 3, 4. Is it? So if in case the current is flowing in one direction, pointer will go right side. If you will change the direction of the current, pointer will go left side. Is it? And 0 will be at the center. Is it? Can you see here? Pointer normally aluminum. You can use other material also depending upon the requirement here. Okay, and here also kindly see. These are the water construction things required. Now we'll see here the working principle. So see, what is the working principle? In the starting of the video, I told you torque equal to mb sin phi. That means when a current carrying coil is placed in a magnetic field, it will experience the torque. Okay, see. When the current to be measured is passed through the coil, it experiences a deflecting torque which is given by, where is the deflecting torque? As I told you very well, when this current will flow, there is the one deflecting torque in a clockwise direction. Okay, so this deflecting torque is given by what? Remember that here, this deflecting torque, what is the formula I told you? See, mb sin phi. What is m? Magnetic moment. That means NIA. N is the number of turns, I is the current, A is what? Area of cross section of the coil, into B into what will come here? Sine 90 degree, because of the radial magnetic field. So here what will happen that here you can see very well, this deflecting torque will come here, what? NIAB. What is this? This is the deflecting torque. Is it? Great. Now after that what will happen that here, the moment deflecting torque will come, at the same time restoring torque will also come, because the pointer should be in a equilibrium static situation. Then only we can see the reading, otherwise it will keep on oscillate. We can't take the reading. Okay, so see, as the coil rotates, the spring gets twisted, and as a result of it, a restoring torque develops in the spring, which is given by here. Where is the restoring torque? Let's see here. Deflecting torque clockwise, restoring torque in which direction? Anti-clockwise direction, because this spring is there now, this spring will get twisted. Okay, great. So this restoring torque is given by what here? Remember that, see, this tau r is given by k into theta. Okay, so what is the k? See, where k is torsional constant of the spring, that is restoring torque per unit twist. Okay, and what is theta? Theta is the angle of twist or deflection angle. Okay, so don't be confused in phi and theta. Phi is angle between M and capital B, theta is the angle of twist. Is it? Great. Now let's see here. At equilibrium position, what will happen? Let's see. In equilibrium position, the deflecting torque is equal to the restoring torque. So mathematically, what can we tell? See, that means this restoring torque will be equal to what? Deflecting torque. Is it? So let's see here. What is the restoring torque? It is given by K into theta. And what is the deflecting torque? See, NIAB. NIAB. Is it? So from here, if I write here the, let's take for example I. So what will be the I? You can see here, this will be given here, K by NAB into theta. Now, can you see very well? NAB will come this side, so I equal to K by NAB into theta. Hence, what we can write here? Here we can write here, see. So, I will write here, see, this I will become here what? I will become here. This is the G into theta. What is I? I is given by G into theta. Now, if you compare, what is the value of the G? G will be given here, see, G equal to K by NAB, or we can tell what? I by theta. Okay. What is G? G is K by NAB, or this one here, see. Hence, G equal to, see from here, I by theta. Okay. Remember that, please. Or what we can tell? K by NAB. Now, and what is G? As I told you, see, G is called galvanometer constant or figure of merit. Very, very important, figure of merit. What is N? N is the number of turns in the coil. Okay. What is A? A is the area of cross section of coil. And what is B? B is the magnetic field. Is it? Can you see here? Okay. Now we are going to see what is G. So let's see. The topic is what? Important terms related to moving coil galvanometer here. Okay. So under this you can see here figure of merit. What is figure of merit? See, it is defined as the current which produces a deflection of one scale division in the galvanometer. It is given by, so what can we write here? The value of G. So G will become here, we can see here, see. What is G? G is given by I by theta. Is it? So see, this is the figure of merit also. So G equal to what? I by theta, or what can we tell? K by NAB. What is this called? This is called here the figure of merit. Important. Figure of merit. Okay. And what is the unit? If we talk about here the unit of the figure of merit. So see, I by theta. What is I? Current. That means ampere per division. Ampere per division. That means for one division, how much current is flowing? Figure of merit. Okay. Next one, let's see. Second one is what here? The current sensitivity. Important. Definition used to come in exam. So see, it is defined as the deflection created in the galvanometer per unit current, and it is given by here. Okay, so current sensitivity, that means we can write here IS. It is given by what here? Again, see, deflection created in the galvanometer. That means we can write here, see, theta per unit current. That means what? Theta by I. This is called what? Current sensitivity. So you can see just it is the reverse. So theta by I will be what here? You can see very well. NAB by K. Okay, or we can tell 1 by figure of merit. Figure of merit here. Is it? Remember that here. Okay, and we can write here in a box. Okay, see. This is called what? Current sensitivity. Now you tell me how to increase the current sensitivity. Sometimes question will come. So remember that here in this situation, how to increase the current sensitivity. To increase the current sensitivity, that means if you want high current sensitivity, the K should be small. K should be small, or N should be high, or A should be high, or B should be high to increase the current sensitivity. Is it? And what is the SI unit of the current sensitivity? See, theta means what? Angle, radian. And what is I? Current. That means we can write here, see, radian per ampere here. Is it? This is called what? Current sensitivity. Is it? Great. Now let's see, students, the next one is what here? The voltage sensitivity. So see, what is this? See, it is defined as the deflection created in the galvanometer per unit voltage. Okay, and it is given by what here? See, this voltage sensitivity. That means I can write here Vs. It is given by what here? See, theta by V. Okay, or theta by I into R here. Is it? Because from the Ohm's law. Now, current and resistance. So here I can write here what here? 1 by R, and what is this? This is the theta by I. Okay. And what is theta by I? That is the current sensitivity, is it? So we can write here, see, this is the 1 by R, and what is the theta by I? You can see very well, it is given here what here? NAB by K. Okay, what is this here? See, NAB by K, and this will give us what? This will give us voltage sensitivity, is it? What is the SI unit? That means here radian per volt, SI unit. What is the relation? As I have told you very well, see, it is given by voltage sensitivity, and what here? 1 by R into current sensitivity here, is it? So Vs equal to 1 by R into Is, is it? Remember that. Now, after that, the most important thing is what here? See, note, voltage sensitivity is independent of number of turns of coil. Again, I am telling, independent of number of turns of coil, while current sensitivity depends upon it. How can we tell one by one? See, if I write here the current sensitivity, that means Is. Current sensitivity, what is the formula? You can see very well here, NAB by K. What is this? NAB by K. So here what will happen that here? See, this current sensitivity I can write here directly proportional to N. Depends, is it? But if I talk about here the voltage sensitivity, what is the formula? Kindly see here, see from there. NAB by KR. That means we can write here, see, voltage sensitivity is directly proportional to N by, this R is the very, very important, N by R. That means you know what will happen that here, in this formula, remember that here, the moment you will increase the value of N, R will also increase in the same proportion. Why? Because see, the moment you will increase the number of turns, the length will also increase, is it? And one more formula is there, you can see, R is directly proportional to L, or we can tell directly proportional to N. So what can we tell here? The moment you will increase the number of turns, what will happen that here? Length will also increase. The moment length will increase, what will happen that here? This R will also increase. That means N and R both are interrelated. That means when N will increase, R will increase. Similarly, when N will decrease, R will also decrease, is there, is it? See, it will decrease also. That means here you can tell very well here in this situation, N and R both are interrelated. So when you are changing the number of turns, the voltage sensitivity cannot be changed because resistance will change in the same proportion. Okay, remember that here. Independent of number of turns, because N and R will change in the same proportion. After that, let's see, very, very important points related to MCG, as I told you also. So see, first one, it is very sensitive device. It gives a full scale deflection for a current of the order of microampere, very small, 10 to the power minus 6 ampere. Some books they can tell 10 to the power minus 9 ampere also, but anyhow very small current. That's why there will be need to convert the galvanometer into ammeter or galvanometer into voltmeter. We will see in a further videos. So galvanometer to the ammeter, we have to connect low resistance in a parallel for bypassing the high current, and galvanometer to the voltmeter, we have to connect high resistance in series. In next videos we will see. So coil may get damaged if large currents are passed through it. So anyhow, very sensitive device, very small current. If in case high current is flowing and you have not provided any shunt, is it? That means low resistance in parallel, then what will happen? The coil may get damaged also. So very sensitive. Next one, see. It is having linear scale because deflection is directly proportional to the current. What I have told you, see, we have seen I is directly proportional to theta is there. That's why which scale? Linear scale is there. It is going to measure the DC. What it will measure? DC, it will measure direct current. Later we will see hot wire instruments are there. They will measure the alternating current and their scale will not be linear. Why? Because this instrument will be based upon the magnetic effect of current. But to measure the AC, that means hot wire instrument, their deflection directly proportional to the heating effect of the current. That means in a moving coil galvanometer, theta directly proportional to I. But in a hot wire instrument, theta is directly proportional to I square from the Joule's law of heating, because H equal to I square RT. Okay. So what is this I told you? I directly proportional to theta. Here I am telling you this moving coil galvanometer is based upon which effector? That is based upon magnetic effect of current. Which effector? Magnetic effect of current. And what I have told you, one more thing, for measuring the AC, what will be there? Hot wire instruments, that is based upon what? A heating effect of current. What is this? A heating effect of current. Heating effect. Okay. And here what will be there? This theta will be directly proportional to I square here. Okay, from the Joule's law of heating. Okay, so I hope so. This thing and this thing is very clear to you. Okay, MCG, magnetic effect of current, will measure DC. Hot wire instruments based upon heating effect of current, and it will measure water. It will measure AC, for AC, alternating current. Okay, remember that here. Third one, as I told you very well, see, radial magnetic field. Radial magnetic field, how to get it? Concave shaped magnet, that means phi should be how much here? 90 degree. And soft iron cylinder, that means ferromagnetic material, mu r how much here? Greater than 1. Okay, so let's read again. Radial magnetic field and soft iron cylinder is used to increase the sensitivity of MCG. Is it? So see here. So students, I hope so. This video, in which we have seen working principle, construction, current sensitivity, voltage sensitivity, and important terms, is very clear to you. Okay, keep studying, keep growing.